first try to do some basic analysis first. Okay, the trapezoidal map of a set S of n line segments in general precision contain at most 6n plus 4 vertices and at most 3n plus 1 trapezoids. Okay, 6n plus 4 vertices. Okay, 3n plus 1 trapezoids. That means the linear number of vertices and the linear number of trapezoids. Okay, so how can we have such a conclusion? Okay, first, okay, let's look at the vertices. Okay, in the trapezoid map. Okay, this. Okay, in here. Okay, the vertices. Okay, could be. Okay, like for example, this one, which is part of the bounding box, or this one, which will be offered by the endpoint of the segment, or it could be something like this one, and this one, because these two originally they are not vertices, but because we introduced this vertical line, so these two becomes the new vertices. Okay, so we need to take into account these three different types, right? Okay, so the first type is an a vertex of R is a bounding box. So there are 4 of them to be exact, right? 4 endpoints. So 4 edges of the bounding box, right? And then an endpoint of a line segment. Okay. So since we have n line segment, okay. So the total of endpoint will be at the most 2n, right? You may ask, why do I say at most? Because there may be some endpoints that are shared by more than one line segment, right? Okay, such as you could have the 2 line segments like this. Okay, this endpoint is shared by these 2 line segments, right? But this is okay, right? This is okay. Okay, in our assumption, okay, I say like okay, no 2 endpoints share the same x coordinate value, right? But this is one endpoint. It's just like this endpoint is shared by 2 line segments. Okay, so this does not violate our assumption. Okay, so so if we have n line segments, we have at most 2n endpoints, right? So this situation, okay, in this situation, because some line segments, some endpoints may be shared by some line segments. So the 2n endpoints will be upper bound estimate, right? It's an upper bound estimate. If we have such a situation, okay, we don't have 2n endpoints, right? We maybe have like a less than 2n line endpoints. But anyway, okay, so the total number of endpoints is bounded by 2n. Okay, and also the point where vertical extensions starting in an endpoint, okay, intersect, okay, on another line segment. Okay, so for this situation, okay, for each endpoint, it can only contribute at most to such intersection, right? Okay, so for each endpoint, okay, it can contribute 2 additional points at most. Okay, so it will be, total will be 4 plus 2n plus 2 times 2n, okay, equal to 6n plus 4. This is the upper bound. This is the upper bound. Okay, this is not exact number. This is the upper bound, by the way. Okay, so 6n plus 4. You can see that it is linear to the number of line segments. Okay, so how about the number of trapezoid? Okay, number of trapezoid. Let's concentrate on the left P. Okay, remember we discussed the left P situation previously, right? There are actually 4 different types of left P, right? One is a degenerate case, and one is like the left P is offered by the top, but it's like the left endpoint, right? Okay, the other one is the left P. I'm sorry, left P is offered by the right endpoint of the top segment, or the left P is offered by the right endpoint of the left endpoint of the bottom. Okay, only one case is offered by the right endpoint, right? Okay, which is the last case, right? So you can see that, okay, for every trapezoid, okay, it's either the endpoint, okay, if you look at the left P, it's either the endpoint of a segment or the lower left corner of R. Okay, lower left corner of R, I mean, that's also like, okay, because like here. Okay, the only special case is this one, this trapezoid. This trapezoid, its left P is this one. Okay, it's this one, but this is a special case. The other situation, okay, it's always offered. It's always like happened by the endpoint. Okay, we discussed this by these 4 situations previously. Okay, so it should be obvious. Okay, so let's consider all of them. Okay, all of them. Here. Okay, so the left endpoint of a segment can be left P for at the most 2 trapezoids. Okay, because like if you look at here, this one, okay, this one, okay, this is this left endpoint is the left P of this trapezoid. It is also the left endpoint of the top trapezoid. Okay, because this one you also have an extension, vertical line to the top, right? So this top, I mean we have another trapezoid on the right here. Okay, so this left P, this left endpoint is used as a left P for both this trapezoid and the top one. Okay, and that's the most case. Okay, that's the most case. Okay, here, left endpoint of the segment can be left P for at most 2 trapezoids, and the right endpoint of a segment can be left P exactly once. Okay, exactly once. Okay, because it will be something like here. Here. So this right endpoint is used as left P here. End of story. Okay, it cannot be used as a left P for anything else. Right? Okay, so based on this discussion, okay, so total number of trapezoids will be at most, okay, one is where? One is the left corner of R, okay, so that's where the 1 comes from. And because for each left point, okay, it can be used for at most two trapezoids. So we have 2n, okay, for the left endpoint, and we have 1n for the right endpoint. So total is 3n plus 1. Again, this is our bound. So it's at most 3n plus 1. Okay. So this one tells you that if you have n number of segments, okay, and you try to create a trapezoidal map, okay, then you are going to end up with linear number of trapezoid and linear number of vertices. Okay. So in the following, we have this. We need to prove that the algorithm trapezoidal map, okay, computes the trapezoidal map, okay, T of S, okay, of a set of n line segments in general position and a search structure D. Okay, their search structure D is the tree-like graph, okay, for T of S, okay, in big O n log n expected time, okay. Be very careful. This is expected time, okay, and expected size of the search structure is big O n, okay. It's linear, okay, and for any query point Q, the expected query time is big O log n. Okay, so if you look at here, okay, so we use, this is like expected time, expected size, expected query time, okay? So in the worst case, it may be worse than that, okay? But the expected time, expected storage space or expected query time, okay? You can treat them as the average case, okay? Average case, okay? So compared with our intuitive approach, okay? Well, our intuitive approach, okay, the query, okay, the worst case is log n, okay, so it's actually, it has a faster query guarantee, okay, but the issue is the search structure, okay, the storage cost is n squared. Here, our expected search structure complex is linear, so it's pretty good. It's pretty good, okay. But how do we prove it? Okay, this proof is, you know, later. Okay, you are going to see some proof kind of similar to this one. Okay, so I hope this one serves as a foundation for you to understand, like follow the future like proof. Okay. So first, okay, one thing I would like you to bring your guys' attention is like this. When you add a line segment, okay, let me ask you, okay, how many additional depths normally will be introduced in the worst case scenario? For this one, you can see we replace this by this, right? So what is the additional depth?深度是不是加2 right? Because original we are here. Now we have, this one and this one, right? Okay, so this one is like worst case, right? But the depth increased by 2, right? But this is not the worst case. The worst case is actually something like this. Okay, originally we have one node. Now, because this node is replaced by this one, so depth will be increased by 3, right? Right? Okay, from here to 1, 2, 3, right? So the depth will be increased by 3. That's the worst case, right? That will be the worst case. It couldn't get worse than that. Okay, couldn't get worse than that. So every time you add a line segment, okay, the tree depth can grow as worse as 3 depth. I mean, 3. Okay. So having after this observation, let's start this discussion. Okay. That xi, this xi is the random variable. Okay, it's a random variable. Okay, this xi, okay, denote the number of nodes on the search path created in iteration I. Okay, so say we are searching for a particular point. Okay, we are searching for a particular point, and we go through some a path, right, to find like which trapezoid contain that point, right? Okay, and then okay, we need to think, okay, this path, okay, the node that the path, this search goes through, okay, this path must be created through these iterations, right? Through these iterations. So let's assume, okay, xi to be, the ith in the ith iteration. Okay, when we add the segment I, si to this structure, okay, the added node, okay, happen to be in the search space, in the search path. Okay. So let's look at this expected length here, because this expected length is our query time, right? Okay, it's our query time. The query goes from the top to one of the leaf nodes, right? So that's depending on how long this path is, we have the expected query time. Okay, so this expected query length is this, right? So expected length. Okay, and we can put this e to the inside of this. So it's going to be summation. Okay, I from 1 to n expected xi. Okay, expected xi. So this expected xi means like at iteration I, okay, how many nodes are added in this search path? Okay, number of nodes added in this search path. Okay, so that pi denote the probability that there exists a node on the search path of Q that is created in iteration I. Okay. Okay, then we have this one. This one is small or equal to 3 times pi, right? Okay, so if this iteration I does affect this search path, okay, if this iteration does affect the search path, okay, say that is the probability pi. Okay, that's a probability pi. Then it increase the search path by at most 3, right? Okay, so 3 times our pi will be this one, right? Okay, but why is this small or equal? Okay, because that's the worst case scenario, right? Because you can see here, this is the worst case. If the search path is here, yeah, that's you increase by 3, right? But if the search path is here, you increase by only 1, right? If your search path is here, you increase by 2, right? Or the next page. In this scenario, okay, yeah, the search path, if the search path is one of them, so the increase will be at most 2, right? So here we are trying to consider the worst case scenario, so it's 3. 3 is the worst case, right? So you couldn't be worse than that. So it's going to be small or equal to 3 times pi, okay? Okay? Because the other case it will be either 1 or 2, right? You're only going to add like a path by 1 additional or 2 additional depths. Okay. But the worst case, I mean, you may add like 3 additional depths. So this is the worst case. Okay, consider like at one iteration. Okay. So iteration I contribute a node to the search path of Q. Okay, exactly if this delta Q in Si minus 1, okay, the trapezoid containing Q in, before you add the segment Si, the trapezoid contains Q, okay, it's not the same as the trapezoid contains Q, okay, after adding the Q, Si, right? It will be different. Okay, for example, okay, you can see here. Okay, say the Q is here. Then this trapezoid, original is this one, right? Now it's gone. This one is gone. It becomes like some smaller ones, right? Right? So it's going to be different, right? Okay, same thing. Okay, if the trapezoid, before we add Si, okay, assume that Q is here. Is here. Now, after finishing the adding of the Si, okay, this delta 3 is no longer there. Okay, it's replaced by this E, F, and part of the C, right? Okay. Okay, so it'll be different, right? So that's what we are talking about here. Okay, it's not the same as the trapezoid. Okay, that contain Q after we add the Si. Okay, so the probability Pi is going to be this probability. Okay, the Q, you know, in Si, okay, after we add like the segment Si, okay, the trapezoid contains Q. It's different from the trapezoid, okay, that contains Q, okay, before we add Si. They are different. What is the probability here? So we need to discuss this probability. So now, okay, because, okay, from Si minus 1 to Si is a little bit more tricky. It's difficult. So let's consider this problem in a different way. Okay, in the backward thinking. Okay, we are considering this problem in the backward thinking. Okay, so when removing Si, okay, from this capital Si, okay, it's going to result in the change of delta Q Si. What is the situation? Removing the Si is going to change that particular trapezoid that contains Q. Okay, because, okay, the only case, okay, the only few cases, okay, removing that segment, okay, is going to affect the trapezoid that contains Q is, okay, that segment Si happen to contribute to the top, bottom, left, or right of the trapezoid that contains Q in the Si, right? Right? Okay, so for example, let me again use this. Okay, so remember I say like, say Si is here, right? Si is here. So SI is here, okay? So removing this, because this is SI, this is SI. Removing this SI is going to destroy this trapezoid. Why? Because this SI contribute the bottom of this trapezoid, right? Okay? Or if it's inside here, if it's here, then removing this trapezoid, this SI is going to destroy the right P of this trapezoid, right? Right? And so on. Okay, you can see what I'm talking about. Okay. Same thing apply here. Okay. Say like if the P is here. Okay. After adding the SI, that point is here. Okay. But removing SI, okay, this F will be gone. Why? Because this SI actually contributes the left P of this trapezoid, right? Okay. So that is when removing SI will result in the change of this delta Q SI. Okay. Okay. So because like the top, bottom, left P, right P. Okay. So what is the probability segment offer the, for example, let's consider just one of these cases, okay? The top of the trapezoid. What is the probability the segment contain? The segment provide the top of the trapezoid. This SI provide the top of this trapezoid. Well, remember now we have I segments, right? We have I segment, S1, S2, S3, up to SI, right? Okay, because each segment has the same probability to be the top of this trapezoid, right? So it's I, 1 over I, right? I 分之一啦. Okay? But we have these four cases, right? Top is 1 over I, bottom is 1 over I, left P is 1 over I, right P is also 1 over I, right? So total will be what? Total will be 4 over I, right? So, okay, so Pi equal to this one equal to, it's a small equal to 4 over I. Okay? And then you can, okay, using the above formula, okay, this path, when we estimate like the average or the expected length of the search path, is going to be small equal to 3, summation of 3pi, which will be small or equal to, because pi, as I said, is like a 4 over I, right? 4 over I, so it's going to be small or equal to 12 over I, right? 12 over I. You can get the 12. Put the 12 in the front, and it's like I from 1 to n, I 1 over I. This is a harmonic series, right? Harmonic series. You know, like a harmonic series is like it's bounded by log, right? This is a log n. This is log n. It's bounded by log n. If you don't know about this, you need to check like first year calculus. Okay, the calculus will teach you this. Okay, if you have any question, check your calculus textbook. Okay, how to convert this one to be log n. Okay, this 12 is a constant, so don't worry about that. So you can see that the expected query time is big over log n. Okay. Then we need to check the worst case storage complexity. Okay, worst case storage complexity. Okay, so the total number of nodes that required for our tree-like algorithm, okay? Tree-like graph, okay? It's going to be big O(n). Where is this big O(n) comes from? Okay, remember we said that there are how many trapezoids can we end up have? Like after adding n line segment, how many trapezoids at most can we have? 3n plus 1, right? 3n plus 1. We talk about that here, right? 3n plus 1, right? So for each of these trapezoids, okay, it will become one leaf node, right? Kind of like leaf nodes in our graph, right? It's going to be, you can see, each of these trapezoids become kind of like leaf node here, right? So those leaf nodes add up to be at most 3n plus 1, right? So those will be big O(n), right? Big O(n), okay? That's where the big O(n) comes from. Okay, but the other one will be the number of inner nodes, all the inner nodes. The other will be all the inner nodes. Okay, inner nodes. So here we can break those inner nodes into like I different cases, because like those inner nodes may be created at different iterations, right? At different iterations. So we say like okay, this number of inner nodes created in iteration I, okay, we add up from 1 to n, so that will be the total number of inner nodes, right? Okay? So the leaf nodes plus inner nodes will be the whole graph, right? The whole graph. Whole tree-like graph. Okay, whole tree-like graph. Okay? So let Ki be the number of new trapezoids that are created in iteration I due to the insertion of segment Si. Okay. The number of inner nodes created in iteration I is exactly Ki minus 1. Okay. Why do I say that? Okay, let me use this to show you. Okay. Okay, you see, these are the new leaf nodes or new trapezoid that's created after the insertion of Si, right? This A, B, C, D, E, F. These are the new trapezoid created after the insertion of Si, right? Okay, so how many internal nodes do we create here? A, B, C, D, E, F. We have 6 trapezoids. And you can see we have 1, 2, 3, 4, 5. 5 internal nodes. Okay. One moment. My mom called. 喂，我在上课，我等一下再回你。Okay, so 6 new trapezoids, 5 internal nodes. Okay, so look at this case. Okay, adding this Si, we have 4 new trapezoids, right? How many internal nodes? 3, right? 3 internal nodes. So the number of internal nodes is always 1 less than the number of new trapezoids. Okay? It's always like that. This actually can be proved like, formally, okay? But I don't have time to talk about the details, so I'll just like, show you by this example. Of course, this is not a formal proof, but just to give you some idea. Okay? So if we have Ki, if this iteration I create like a Ki number of like trapezoids, okay, then we are going to create like Ki minus 1, this many number of internal nodes, Okay, so worst case upper bound of Ki, okay, follows from the fact that the number of new trapezoids in T of Si can obviously not be larger than the total number of trapezoids in this one, right? Which is bounded by linear, right? Okay, remember, like if you have n line segments, it will be 3n plus 1, right? Okay, okay, so you add in the new line segment, we are going to end up having I segments here, right? So total number of trapezoids will be 3i plus 1, at most 3i plus 1, 3i plus 1, right? So that's, of course, that's a very, very generous estimate, right? Very, very generous estimate. So, but nevertheless, that's like, that's big OI, right? Okay, big OI. So you are going to have like a big O and this one. You are going to have big O n plus summation I from 1 to n, big OI. Okay, so this one, okay, if you add them up, okay, basically it's just like you are adding 1 plus 2 plus 3 plus 4 plus 5, blah, 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 plus n. You guys know how to do that, right? It's going to be n times n plus 1 divided by 2, right? Okay, so that's pretty much, n squared, right? N squared. So you know, like the worst case storage complexity is this one, okay? So this, in the worst case, the storage complexity is going to be as good, as bad as our intuitive approach. Intuitive approach. Remember the previous one, like it's still n squared, but in reality, okay, the average case is really not like that. It's big O n, just big O n y. Because now we consider expected storage complexity, or we can use this E, right? We can use this E, okay? This expected, on the top, okay? So this one stays to be linear. This one, I mean, because this indicates like the number of trapezoids, right? Number of trapezoids is still n 3n plus 1, right? So we don't change that. This is number of leaf nodes, okay, which is still linear. This is number of internal nodes, okay? So this Ki, let me remind you, Ki indicates the number of new trapezoids created after the insertion of the Si, segment Si. And of course, I mean, Ki minus 1 is the number of internal nodes created by adding the Si, okay? So this, we want to see like this expected size. Okay, so this minus 1, okay, minus 1, okay, if you use like a summation, it's going to be add up to be n. So it's not going to change our order. So we are just going to concentrate on this E of Ki. Okay, E of Ki, because like the other part doesn't affect the complexity. Okay, so for a trapezoid, okay, and a segment S, okay, that delta, this smaller delta S, okay, to be 1 if this trapezoid disappear when S is removed from Si, 0 otherwise. Okay, we use this way to do the estimate. Okay, then, okay, think about this. There are at the most 4 segments that causes a given trapezoid to disappear, right? Okay, this is exactly the same argument we used previously, right? Because the trapezoid contains top, bottom, left P, right P, right? Okay, so of course, okay, some segment provide top P and the left P, top and the left P. Okay, it could be the case like that, right? It could be the case like that. For example, like here. Here, you can see this segment. It is the top of this trapezoid, but it also provides the lab P for this trapezoid, right? Okay, so this, but you know, a little bit more generous assumption is that, okay, assuming all this trapezoid, okay, all the sides are determined by by different trapezoid, by different segments. That's worst. That's actually the worst case. That's actually the worst case, right? Okay, the worst case. So, if you add up everything here, removing S is going to remove this delta. Okay, so of course, like you are going to count like this number of trapezoids, like you know, more than a number of several times. Okay, so it's going to be bounded by 4 times this one, right? Because as I said, 4 is already the greatest possible situation, which means like all 4, like top, bottom, left P, right P, are contributed by different segments, right? But in the real situation, I mean, they may be shared by less than 4 segments, right? But if you consider they are from different different segments, then this one is the upper bound. And this is one is the upper bound. Okay, so but we know this one is the number of trapezoid. This is number of trapezoid. This number of trapezoid, okay, as I say, okay, since we are adding I line segments, so this one is bounded by 3i plus 1, right? 3i plus 1. This is bounded by 3i plus 1, right? So 4 times 3i plus 1, of course, it is still linear, right? It is still linear. Okay? This one is still linear. Okay? So, using the above formula, okay, we have the expected Ki is going to be 1 over I, okay, this one. Why is 1 over I this one? Because like you don't know this I iteration, because you don't know, because you are trying to average over these iterations, because totally you have from 1 to I iterations, right? 1, 2, 3, 4 up to Si, right? And that's the total number of internal nodes that you have. But you don't know, I mean, the internal nodes you have for this, for one iteration, okay, you can only assume like each iteration have the same impact, right? Have the same impact. So you just do the average, okay, 1 over I. Okay, because you don't know like which segment contribute more, contribute less, right? So the easiest way is, okay, for each segment, each time you add one segment, it has the same effect, right? Because we are doing this as an expected or average case, right? So we just average them. Okay, so we can multiply this by 1 over I. So, but we know that this one add up to be big OI, right? So it's going to be big OI divided by I, right? This big OI divided by I, well, I know this is not a formal mathematics notation, okay? If the mathematics people see this formula, they are going to kill us, okay? Because apparently this is not a formal way to write the big O, okay? But you get an idea, okay? This one is roughly constant, okay? So in other words, every time you add a new segment, okay, the number of internal nodes you add to this searchable structure is a constant. Okay, on average, of course, on average, or expected, or average it's a constant. So of course, like then if that's the case, okay, then you put this back. You put this back to here. I'm sorry. Put this back to here. This one is an expected storage. It's going to be big O n plus summation constant. Okay, so I plus 1 to n a constant. So this add up to be a linear cost as well, right? Okay, so the both terms will be linear. So of course the whole thing will be linear. So the expected storage complexity is going to be linear. Okay? Okay? Okay, so I have explained the expected query time. I have explained the expected storage cost. Okay, now, okay, the last one, the expected time to